So here in a vessel you are having two liquids of densities rho 1 and rho 2, having these levels are H1 and H2 respectively, and the area of base of the tank is much greater than the area of the orifice at the bottom of tank. Now, in this case, find velocity of efflux. V, that means the liquid, find velocity of the liquid V, which comes out of the hole at the bottom. So here also we will apply Bernoulli's and the continuity equation as usual. So let us consider a streamline like this, and let's consider points 1, 2 and 3. There are 3 points here: point 1, point 2 at the junction, and point 3. Okay, now so velocities are v2 here and v3 here and v1 here. That v1 is equal to v, velocity of efflux, and the streamline, the fluid is moving along this given arrow. So we apply the continuity equation first. The continuity equation, see capital A, say if small a is area of the hole orifice, and capital A is area of the base of the tank. So we can write from continuity equation capital A into V2 equal to capital A into V3, both are same, equal to small a into V. Now as A, capital A much greater than small a, we can neglect both V2 and V3, and also however small they may be, V2 is equal to V3, right? So that part is solved from continuity equation, and next we apply the Bernoulli equation. So as you know, the Bernoulli equation is applicable for a single fluid. So first consider the streamline from point 2 to 3, or say point 3 to 2 rather. If you consider the direction of the flow, then point 3 to point 2. First we consider that 3 to point 2, then next we'll consider 2 to 1. 3 to 2, P3 plus half rho V3 square plus it's rho 2, right? Rho 2 G. You can choose a reference level. Say for this problem, you can choose the reference level here. So plus with so uh, for these 3 to 2, you can choose reference level at the junction between the two liquids of densities rho 1 and rho 2. So rho 2 GH2 is equal to P2 plus half rho 2 V2 square plus rho 2G into 0 with respect to that reference frame is 0. So P3 is P naught because that end is open to atmosphere, and V2 is equal to V3. So you can cancel that term. So therefore we can write P2 P2 is equal to P naught plus rho 2 GH2. So there we have calculated P2. Now next we'll go for the streamline uh, for points 2 to 1. So from 2 to 1, so P2 plus half rho 1 this time. 2 to 1, the liquid is having density rho 1. V2 square plus rho 1 G. Now, here for this problem, we'll take, for this case, the reference we can shift to the bottommost point, bottommost line. Reference can be shifted as per your convenience. So rho 1 G times H1 equal to P1 plus half rho 1 V square plus rho 1 G into 0. So point 1 is at the reference level only. So height is 0. Now P1 is same as P0 because 1 is open to atmosphere, and P2 we have calculated already, P0 plus rho 2 GH2, and V2 you can put to be 0. Therefore, what you have, half rho 1 V square is equal to rho 2 GH2 plus rho 1 GH1. So therefore, we can find V as, therefore V is equal to root over 2G multiplied by, so H1 plus H2 rho 2 divided by rho 1. So this is the answer. This is the velocity of a flux of the liquid coming out of the hole at the bottom. Now in the same problem, we could have done it in a different way. So this is height H1, the liquid above, that's height H2. So we can convert this yellow liquid, that is we can convert liquid 2 to liquid 1 so that it exerts same pressure. So that means, so rho 2 GH2 is equivalent to rho 1 GH2 dash. So that means if you replace, that means, so this figure is equivalent to, if I draw this thing filled up with this liquid, so downward you have this H1, already you have this H2 dash. So make the total liquid as the liquid of density rho 1. That also could have been done. So there it is, orifice here. So this total liquid is having density rho 1 and height, then this V, you could have calculated V as root over of 2G into H1 plus H2 dash, where this H2 dash you can calculate H1 plus, see, from this equation above we can calculate H2 dash is rho 2 H2 by rho 1. So plus rho 2 H2 by rho 1 this way. So in this way you can extend this to 3 or 4 liquids like that. So that means, say if you see, instead of 2 liquids you can have 3 liquids of, say, density rho 1, rho 2, rho 3 and heights H1, H2 and H3 respectively. Then you can find out the speed V as root over of 2G into H1 plus rho 2 H2 by rho 1 plus rho 3 H3 by rho 1, because you have converted the whole liquid into the liquid of density rho 1. In this question number 7, we will discuss about an ancient clock known as water clock. Water clock is a uh, device which is used to measure time. So you have heard about the sand clock. Water clock is some vessel which is having a leak, some an orifice below, and it's filled with water. And the rate of decrease of level of water. So that means there is a change in water level which is uniform with respect to time. That means the speed of the water, the speed, say v dash. So v dash, the speed of decrease in water level is constant with time. So if the speed is constant with time, then so if you make graduations on the clock, then the sorry, so if you make the graduations on the clock, then it will be uniformly covered, this graduations with time, right? So as per uh, data or evidence, the earliest water clock was in China and maybe in India also, but the date is not properly known. Some authors claim that, this I am taking from Wikipedia, some authors claim that the earliest water clock in China was around 4000 BC. 4000 BC. Can you think how, I mean, that time, 4000 BC. It's a long, long time ago. So the hole in the clock is having a cross section, say cross section small a. The area of the hole or orifice is much smaller than the tank, that of the tank, the cross section of the tank. Now suppose I draw the x axis here and the y axis here, right? Now so how does radius radius will be x, right? Radius x of the tank vary with height. Height is y from the hole or from the bottom of the tank in the water clock. That is the question. And to be a water clock, this velocity v dash must be constant with time, so that the graduations are covered in equal time intervals, right? So you can try out this now. You can find the equation. See, exactly means, say this is a, and suppose the height is y, so v dash is dy minus dy dt, that is v dash, and this radius is x, so the cross section is known, and this speed v is root over 2gy. V is root over 2gy, right? So therefore a, small a multiplied by v is equal to pi x square multiplied by minus dy dt, but small a multiplied by root 2 gy is pi x square v dash. Now v dash is constant, so now you can square both sides. What do you get? A square 2gy equal to pi square x to the power 4 v dash square. So therefore y is equal to k times x to the power 4. That is the equation. So for to be a water clock, condition is that y should be proportional to the fourth power of x.